YouTube portrait. Okay, let's start with the next lecture. In previous lecture, we have started with the uncompensated transmission line. Yes, please. In that, we have seen that transmission line can be characterized by four parameters. First is series resistance, second inductance, third shunt conductance, and then shunt capacitance. You can see this is called a two machine model or a symmetrical, which is symmetrical one because I have connected both sides a synchronous machine, and X is the any point in the transmission line where A is a length of a transmission line. So the fundamental transmission line equation can be given by these two equations, and the solution of these two equations is given by V of X and I of X. That phasor V or I of X can be divided into two parts. One is called as the incident wave, second is a reflected wave. So in that beta and Z0, Z0 is nothing but a surge impedance, which is also called as characteristic impedance, and we have considered here lossless line. That's why it is under root L by C, and a phase constant is given by omega under root L by LC, and from that wavelength is equal to 2 pi by beta. So even we have seen this uh, diagram also, that is from source to load side there is an incident wave and which get reflected back again, which is called as a reflected wave, and because of these two waves, incident the interference between incident wave and reflected wave, there will be a traveling wave ratio, and together these two incident and reflected wave can be called as a standing waves. Okay, now let us start with the or let us focus on this characteristic impedance or surge impedance, and then SIL, that is surge impedance loading. In previous lecture, I said you that just read about surge impedance loading. So let's assume that this is the transmission line, okay, and this is the point X on the transmission line, where transmission line total length of a transmission line is a miles, and at this particular point X, I mean from sending A to this point, the distance is X. At this point, let I of X is a voltage wave and current phasor I of X. Right? One is a incident wave, second is a reflected wave. Okay. Here you can see a transmission line drawn as a two wires. At a distance, let X into the line. There is a current phasor I of X traveling through each wire, and there is a voltage phasor V of X between the wires. Now, if Z0 is the surge impedance of the line, normally we call it as a characteristic impedance Z0, that according to Ohm's law, what Z is equal to V by I, that is V of X upon I of X. Okay, this is for what? For the wave moving rightward. For this wave, I can write surge impedance as V of X upon I of X, which is moving in a rightward, right? Now for leftward, it will be exactly in opposite. That is minus Z0 V of X upon I of X for wave moving leftward, right? Now here you can see that again I have considered the same source and then load. Both are connected with the help of some transmission line, right? Source is having a source impedance of like ZS, and load impedance is ZL, and this is a transmission line, and I mentioned that the surge impedance is a Z0. Okay. Now the surge impedance of the transmission line is what? Just we can say V of X upon I of X. That is what I am saying here. The voltage and the current wave of a traveling wave at any point along the line. It is the ratio of V of X upon I of X. It is the ratio of V of X upon I of X. Both are traveling waves at any point. Now, when the traveling wave reaches the end of the line, I'm saying when this traveling wave reaches, like here you have connected the load. When this traveling wave reaches the, or you can say that this is an incident wave, when it reaches to load, definitely it will get reflected back. That is what he's saying. There will be a reflected wave which travel back along the line in the opposite direction. And when this wave reaches the source, when this wave, which is reflected wave, when this wave reaches the source, what will happen? बघा सुरुवातीला काय होतं इनिशियली देर वॉज अ incident wave, right? Incident wave, once it reaches to or before reaches to ZL, before reaches to load impedance, what was the source impedance? It was this ZS, okay, and load impedance was ZL before incident wave reaching to the load. Once it reached to the load, it gets reflected back, correct? Reflect होऊन होऊन कुठे येणार तो? It will add to the source, correct? Now when this reflected wave add to the source, in that case, definitely my source impedance will not be the same. आता change होणार, right? Previously there was only incident wave. V of x upon I of x was the impedance, correct? Before reaching to the load, V of x was different, and once it reached to load, it get reflected back and again add to the source. In this case, V of x is something different, right? So means what, in both cases, impedance will be different, correct? That is what he is saying. When this wave reaches the source, this wave means reflected wave, reaches the source, it adds to the transmitted wave. जो incident wave होता त्याच्यामध्ये add होईल. It adds to the transmitted wave, and now the ratio of voltage and current, that is V of x upon I of x at the input of the line, will no longer be the characteristic or surge impedance. जो आधी होता तो आता राहणार नाही. This new ratio we call it as a input impedance, right? The input impedance of an infinite line, if I consider there is an infinite line. Infinite line means what? Infinite line means the transmission line having a infinite distance, right? In that case, definitely reflected wave will be absent, correct? Now in that case, I can say that source impedance, load impedance, and then characteristic impedance all are same. Or I can say input impedance is equal to characteristic impedance, provided transmission line is of infinite distance. The input impedance of a transmission infinite line is equal to the characteristic impedance, since the transmitted wave is never reflected back from the. Okay. Now normally for a lossless line, I am saying we consider R and G as a 0, right? We ignore it. So in that case, Z0 will be L by C, under root L by C. But for lossy line, you have to consider R and G. So it will be R plus J omega L divided by G plus J omega C. Now from equation 5 and 6, the apparent impedance at any point along the line is, apparent impedance is saying, or impedance at any point. At any point, let at point X, what will be the impedance? एक transmission line है, let this distance is a x mile, ठीक है? At this particular point, let check what will be the impedance. काय असणार? V of x upon I of x. त्या पॉइंटला व्होल्टेज किती आहे, त्या पॉइंटला करंट किती आहे, त्यांचा रेशो घ्या, you will get impedance. So Z of x will be equal to V of x upon I of x. Correct? Now, we have already seen V of x and I of x in previous lecture, this one. These two equations. Solution of a transmission line, general solution of a wave equations. Right? V of x was equal to VR cos beta A minus x plus Z0 I sin beta A minus x. Similarly, I of x. Just put it. Just put it here. I'm taking, see, Z0 into IR is nothing but what? PR, na? Z0 into IR is V. Z into I. Right? So you can see if I multiply inside the bracket, it will be Z0 into IR cos beta A minus x, where Z0 into IR is a VR. Anyhow, I'm getting term VR cos beta A minus x plus J Z0 IR sin beta A minus x. Similarly, in denominator, I of x will be equal to IR cos beta A minus x, IR sin beta A minus x. Right? Now, Z0 of x, or sorry, Z of x is dependent on the value of x. Now, more importantly, if I want to write, see, I can write this v of x and I of x like this way also. Okay, just cos term, sin term, that can be written as a e raised to I theta. E raised to I theta is what? Cos theta plus I sin theta. I sin theta, correct? So this VR, just write it a VR is its magnitude, and this can be written as cos beta A minus x, j sin beta A minus x is what? E raised to, in this case, theta is what? Beta into A minus x. E raised to I theta. Similarly for current, right? That is both V and I have a constant amplitude. Is its amplitude, no? Magnitude. This is written in a polar form like, right? This is its magnitude and this one is the its angle, which is beta A minus x. Or you can even write it as a VR at an angle theta, IR at an angle theta, where theta is beta A minus x, right? Out of VR and IR both are magnitude. The line is said to have a flat voltage profile. Why? Why? Because you can see, even though this, what is the equation? V of x. Need baga. V of x is now I'm writing by VR e raised to j beta A minus x. Correct? Out of VR is its magnitude. Magnitude I'm saying. Now, look at this equation. V of x. Of x means what? This value is dependent on the value of x. Right? The phasor value is dependent on the value of x. X is what? The distance. Right? If I put here x equal to 0, if I put here x equal to 0, this is nothing but my sending end voltage. If I put here x equal to a, this is my receiving end voltage. If I put here x equal to a by 2, this is my midpoint voltage. Right? But in all cases, even for a sending end, for receiving end, for a midpoint, or at any point, or at any x, magnitude is what? Constant. Only angle is dependent on the value of x. Getting me? Magnitude is always fixed to value VR. Similarly, I. Correct? So as magnitude is always fixed, it is constant. त्याला दुसरा शब्द काय वापरू शकता तुम्ही? It is a flat, सरळ, straight, constant. So at every point of transmission line, you will get a same voltage. The such type of line or such type is called a flat voltage profile. Flat voltage profile का प्रत्येक पॉइंटला voltage same असतो. ठीक आहे? So this is called as a flat voltage profile. Okay? While V and I are in phase with each other all along the line, but are rotated in phase. The phase angle between sending end and receiving end is a theta, which is equal to beta into A. Even you can write it as this as a beta. Normally it is what? Beta A minus x. Beta into A minus x is a phase angle, that is theta. Right? But if you put x equal to 0, that is for a sending end voltage. If I want to see, I'll write the same equation again here. Let my voltage phasor V of x was equal to what? Its magnitude was VR, correct? And angle was e raised to j beta A minus x. Similarly, I of x. That's interesting. Is equal to its magnitude, that is IR, angle e raised to j beta a minus x. Okay. If I want to draw the phasor diagram for only sending end voltage and sending end current, for a sending end voltage and sending end current साठी मला phasor diagram काढायचा आहे. Okay. Then what should be the value of x for sending end? 0. Just put it here. Just put it here. So this v of x will be now equal to Vs, because x equal to 0, sending end voltage है तो, right? Is equal to is what? Mod of Vr e raised to j, what will happen? Only beta into a, x is a 0, right? E raised to j beta into a, where theta is equal to beta into a. If I assume it, this is a, okay, the same equation can be written as mod of Vr e raised to j theta. Similarly, if I put x equal to 0 in a current phasor equation, it will be Is is equal to mod of IR, right? E raised to j theta. Fine. Now I will draw the phasor diagram of Vs and Is. Okay. Now before drawing a phasor diagram, I need to consider any one phasor as a reference phasor. कोणाला घेतो? Let voltage is my reference phasor. Vs is my reference phasor. Fine. In that case, Is will be, huh? Is will be in phase or out of phase. I am taking this as a reference phasor. Okay. Means I am assuming this angle as a 0. बरोबर? What about current phasor? Its magnitude is IR. Angle किती आहे? Theta. Means there is a Vs and Is both are out of phase, definitely. Correct? By what angle? By angle theta. Getting me? So in that case, Is will be like this. Magnitude depends on the value of IR and its magnitude or phasor length, you can say. Anyhow, this angle is the theta, which is equal to, can be written as beta into fine. I can say. Okay. The phase angle between sending end and receiving end quantity is a theta, which is equal to beta into a radians. This is only for the naturally loaded line. Naturally loaded means what? When the load connected to the transmission line is exactly equal to the surge impedance load, which is also called as a natural load. In that case only, see, मी काय काढलं इथे VS आणि IS मधला. I think तू थोडासा कन्फ्यूज आहेस. What I have shown here, that phasor diagram between Vs and Is. So what about if you can anyone tell me where will be the VR? where will be the VR? Yes, phasor diagram. If I want to show VR and IR, VR will be in phase with the VS. Depends हा magnitude काय म्हणजे कमी जास्त होऊ शकेल. And similarly, IR will be in phase with the IS. Anyhow, see the angle between these two quantities same म्हणतो मी. V आणि I मधला angle definitely theta असणार. Fine. Now, a line in this condition is said to be naturally loaded. Okay? Naturally loaded का म्हणतो माहिती आहे का? Because I am getting VR चुकला होता. बरोबर आहे ना माझा? नाही 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 वेट तुम्ही जा थोडंसं चुकला. See, when I put x equal to 0, what is my equation for Vs? VR e raised to j theta. ठीक है? Or even this can be written as Vs is equal to VR at an angle theta. Fine. Now what if I put here x equal to a in this equation? What if I put x equal to a? It is a receiving end voltage. I like receiving end voltage. Magnitude किती है? Again same VR. V of x becomes VR. Magnitude is VR at an angle a minus a is a 0. 0 into anything is e raised to 0 is, or anyhow angle, sorry, e raised to 0 no, anyhow angle is 0. Got it? Now look at these two quantities. There similarly for current will also be there. I mean, if IS equation is like this, IS is equal to IR at an angle theta, then IR will be equal to IR at an angle 0. Okay? In this both case, Vs and VR, magnitude is same, VR, but angle बघा दोघांमधले किती आहे. एक 0 आहे तर एक थीटा आहे. इथे एक 0 आहे तर एक थीटा आहे. बरोबर? आता असं ड्रॉ करा. Angle between Vs and VR must be theta. कुठे येईल? Here you will get angle between Vs and VR. This is VR, this is Vs. Angle between Vs and VR will be theta. Bro, na? So even I can say, let me erase this. If it is Vs, sorry, हेच घेतो मी दोन्ही. If it is VR, because see VR at an angle 0 है ना ये, VR at an angle 0, where will the Vs? VR the same phasor length, but angle is theta. So this will be VR. Correct? Now similarly for current, IR, initially draw this reference one at an angle 0. IR is equal to IR at an angle 0. कुठे येईल ते? We are assuming it as a reference phasor, right? So this will be IR. बरोबर? IS कुठे असेल? Shifted by theta. Right? So this is possible. इथे मी काहीतरी चुकलो का इथे VS लिहायला पाहिजे होता. Fine. You can, in this diagram, you can observe that VR and IR both are in phase. Similarly, VS and IS both are in phase. This is possible. This is possible only if the line is loaded at surge impedance. That is at naturally loaded line. Even, even I can say this is possible. This is possible. या फेजर डायग्राम मध्ये तुम्हाला काय कळतं बघा, the phasor length or magnitude of Vs and Vr is the same, right now? Even for phasor length of Is and Ir is also same. म्हणजे हे दोन्ही डिस्टन्स सेम असतो, म्हणजे हे असं घेऊ शकता तुम्ही. These two distance, I have the region, the line phasor length line is the same. This is possible only at a natural loading. In another way, I can say you will get a voltage profile like this. Baga, I'll assume this as a distance x. म्हणजे हा डिस्टन्स आहे, एक्स पण नाही म्हणणार. I'll say this as a distance. Okay, first says if I want to draw the voltage profile. Huh? This will be sending end side. Okay, let's assume that here is the distance. This is a receiving end side. Okay, from sending end to receiving end, I have assumed that the distance is a mile. बरोबर, टोटल 1 किलोमीटरचा ए माइलचा लेंथ लाईन आहे. सो इकडे असेल सोर्स साइड, इकडे असेल रिसिविंग एंड साइड, सेंडिंग एंड साइड, रिसिविंग एंड साइड. फाइन. But if you observe these two equations, Vs and Vr, so obviously here the voltage will be, या पॉइंटला व्होल्टेज किती असणार, सेंडिंग एंड व्होल्टेज Vs, या पॉइंटला रिसिविंग एंड व्होल्टेज Vr. But if you observe very carefully, the magnitude of Vs as well as Vr is the same. Right? Even if you put x equal to let any y z distance, still you will get the magnitude as the same. Only there is a change in the theta according to value of x. Right? You want current theta guy cos theta is equal to beta a minus x. X नुसार theta change होईल, but the magnitude is independent on value of x. Right? So I can say that you will get a same voltage at every point. Right? This is your receiving end voltage, this is your sending end voltage. Okay, so you can see here this is nothing but a flat one, correct na? So in this is called as a flat voltage profile. Fine. This is possible only if the line is loaded at natural loaded. Huh? Apart from this, समजा naturally or surge impedance loading ला तुम्ही तुमचा line load नाही केला, something is different. If I assume let P is the actual loading of the line. P is a actual loading of the line, and P0 is a surge impedance loading, SIL. Huh? If both are equal, means what? The line is loaded actually at SIL. Barabar? In this case only, you will get flat voltage profile. Right? Apart from this, apart from this means what? If let P greater than P0 or P lesser than P0, you will not get flat voltage profile. प्रत्येक पॉइंटला voltage sameness. You may get voltage profile like this. प्रत्येक पॉइंटला voltage level change आहे. Even though no doubt VS and VR both are equal, but between the line voltage is varying with respect to X. Similarly, you may get this also. Okay. Can anyone tell me when this is possible for this case or this case? In this case, voltage बघा between the line is boosted. Voltage कधी boost होतो? If line is loaded under SIL or over SIL. व्होल्टेज लेवल वाढतोय, लोड कमी आहे याचा अर्थ, म्हणून व्होल्टेज लेवल वाढतो. व्होल्टेज लेवल का वाढला? कारण लाईनमधनं जाणारा रिॲक्टिव्ह पॉवर एक्सेस झाला. का? कारण तो रिॲक्टिव्ह पॉवर कंझ्युम करणारा लोडच कमी आहे. दॅट इज वाय. राईट. मीन शॉर्ट दिस इज फॉर पी लेस दॅन PG अँड व्होल्टेज कमी होतोय, फॉल होतोय. का? बिकॉज देर इज अ शॉर्टेज ऑफ रिॲक्टिव्ह पॉवर. लोड जास्त झालेला आहे. देर इज अ शॉर्टेज of reactive power. Means what? If P is loaded more than PG. Okay. The natural load or SIL is given by P0 is equal to, formula for P0 SIL is normally P is equal to V0 square by Z0 square, where V0 you can call it as a nominal voltage, Z0 is your characteristic impedance or surge impedance. Okay. Now what is advantage of operating the line at a natural load is, because of a flat voltage profile, the insulation is uniformly stressed at all points. Okay, this is what the biggest advantage of getting a flat voltage profile. The natural load of an uncompensated line. हे मी अजून कुठे कंपेन्सेटेड बोललोय का? नाही. स्टील माय लाईन इज अनकॉम्पेन्सेटेड. त्याच अनकॉम्पेन्सेटेड लाईनला व्हॉट इफ आय load that uncompensated line at natural load, I'm getting these answers. I'm getting flat voltage profile. Still it is without any compensator. You can get flat voltage profile only if you have loaded that line at a SI. Without compensator also you can get a flat voltage profile. Okay. The natural load of an uncompensated line increases with the square of from this formula. You can see P0 is directly proportional to the V0 square. Okay. This helps to explain. हे तुम्हाला पॅनल इंटरव्ह्यूमध्ये क्वेश्चन विचारू शकतात. पॅनल इंटरव्ह्यूमध्ये क्वेश्चन असंही विचारू शकतात. नॉर्मली सी की इंडियामध्ये मॅक्सिमम जनरेटिंग व्होल्टेज किती आहे? यू विल से 11 kV. Maximum generating voltage is a 11 kV only. Still you can see the lines of 66 kV, 33 kV, 440 kV, extra high voltage बोलतो ना जे आपण, ते कुठून आले? Maximum generating voltage सर 11 kV आहे, but still line are operating at 66, 132 kV. How it is possible? We boost up the voltage level with the help of step up transformer, right? Why? Reason behind? Transmission losses कमी करण्यासाठी. Okay, this is the first reason. This is the first reason to increase the or to boost up the voltage level. Another reason means Another reason you can find in this formula itself. P0 is equal to V0 square upon Z0. Let me consider this as a transmission line, receiving gain, sending gain. This is your transmission line. Okay. At receiving end, obviously, here you will connect a load. बरोबर कळत आहे now loading up a transmission line means what? Loading up transmission line means what? Sending active power through the transmission. बरोबर आता प्रत्येकाला लिमिट आहे या ट्रान्समिशन लाईनचं काहीतरी लिमिट आहे. यू कॅन लोड अप टू यू कॅन लोड दिस ट्रान्समिशन लाईन अप टू SIL only. More than that, आताच मी जसं डायग्राम काढला होता, you will get reduced voltage, right? So any transmission line with or without compensator can be loaded only up to SIL. Fine. And SIL चा formula काय? P0 is equal to V0 square upon Z0. ठीक है? Okay. Let's assume that according to the previous past history of this transmission line, एक 25 वर्ष आधीचा हा ट्रान्समिशन लाईन आहे. And let the SIL of this transmission line assume that P0 is 0.5 megawatt. ठीक है? You can connect maximally let 0.5 megawatt load to this transmission line. Means what? In another you can say in maximally only 0.5 megawatt through this transmission line. ठीक है? मला अजून कंपेन्सेटर वापरायचं नाही आहे. हां what if I want to increase this value? Same transmission line. Same transmission line, I want to increase its SIL. याच ट्रान्समिशन लाईन मधनं मला आता 0.5 नको लेट 1 मेगावॅट पर्यंत पॉवर पाठवायचा. नाही तर तुमच्याकडे पर्याय भरपूर आहेत. नाही एक काम करा 1 मेगावॅट हा तर ओव्हरलोडेड होईल म्हणून तुम्ही काय करू शकता जास्तीत जास्त हे पूल बदला पैसे टाका नवीन ट्रान्समिशन लाईन डिझाईन करा. त्यासाठी नवीन का पोल म्हणा नवीन इन्सुलेटर वगैरे. येस दॅट न्यूली ट्रान्समिशन लाईन आहे दॅट कॅन हँडल अप टू 1 मेगावॅट. हे सगळे कधीची गोष्टी आहेत पैसे असते तर. इवन विथ द कंपेन्सेटर ऑल्सो यू कॅन इन्क्रीज दिस व्हॅल्यू इवन विथ द कंपेन्सेटर. पण मी काय म्हणतो तात्पुरतं मला कंपेन्सेटर वापरायचं नाही. मग काय करता येईल? बुस्टअप 1 मेगावॅट नको ॲटलिस्ट 0.5 0.6 0.7 तरी करून दे. हाऊ इट इज पॉसिबल? Yes, you can see this formula P0 is equal to V0 square upon Z0, where Z0 is always constant. P0 depends on the square of, not only V, it is a depend on square of a voltage. जेवढं तुम्ही व्होल्टेज बुश कराल त्याचा परत स्क्वेअर होऊन तुम्हाला SIL वाढवून मिळेल. राईट. दिस इज वन मोर रिझन टू बूस्ट अप दी व्होल्टेज लेवल. जेवढं तुम्ही व्होल्टेज जास्त ठेवता त्याच ट्रान्समिशन लाईनमधनं तुम्हाला आता जास्तीत जास्त ॲक्टिव्ह पॉवर सेंड करतात. यू कॅन लोड द ट्रान्समिशन लाईन मोर अँड मोर. कोणी इंटरव्ह्यूमध्ये विचारलं तर हे नक्की सांगा. वाय वी बूस्ट अप दी फक्त टू रिड्यूस द ट्रान्समिशन लाईन लॉस एवढं नको. इवन टू इम्प्रूव्ह दी SIL ऑल्सो. टू इन्क्रीज द SIL वी बूस्ट अप द व्होल्टेज लेवल. ओके. The natural load of an uncompensated line increases with the square of a voltage from this equation number 1. This helps to explain why transmission voltage have increased as the level of transmitted power has grown. म्हणजे म्हणून कारण हे की डे बाय डे आता 2022 आहे एवढं लोड आहे आपल्याकडे. तुम्ही यू जस्ट इमॅजिन 2050ला किती लोड असेल. करेक्ट. प्रत्येक वर्ष 2 वर्षानंतर लोड वाढतच चाललेला आहे. बट स्टील यू कॅन सी ट्रान्समिशन लाईन तेच आहे. प्रत्येक वर्षाला लोड वाढलं म्हणून नवीन ट्रान्समिशन लाईन बसवा असं काय होत नाही. So we have to boost up the voltage level, or you can use the fax devices. प्रत्येक वेळी नवीनच वस्तू विकत घेणं हा पर्याय नाही. The surge impedance Z0 is a real number. Therefore, at natural load, the power factor is a unity, because even at SIL, VS was VS and IS both were in phase. VR, IR both were in phase. Means what? Angle between VS IS is 0. You will get a unity power factor at both sending end as well as at receiving end. Therefore, at a natural load, the power factor is the unity to all points along the line, including the ends, sending end, receiving end. It means that at a natural load, no, unity power factor आहे बरं का. It means that very important point म्हणून मी 3 स्टार केलेला आहे. हे पण तुम्हाला म्हणजे हा स्टेटमेंट पण तुम्हाला मे बी फायनल इंटरव्ह्यूला कुठे टेक्निकल कंपनीज असतील तिथे युजफुल पडेल. इट मीन्स दॅट ॲट द नॅचरल लोड नो रिॲक्टिव्ह पॉवर हॅज टू बी ॲब्झॉर्ड ऑर जनरेटेड ॲट आयदर एंड. तुम्हाला काही गरजच नाही हो कंपेन्सेटरची. जर तुम्ही ट्रान्समिशन लाईन नॅचरल SILला लोड केला तर तुम्हाला एक्स्ट्रा इंडक्टर किंवा कपॅसिटर कनेक्ट करायची काहीच गरज नाही. तिथे काय होतं, रिॲक्टिव्ह पॉवर बॅलन्स असतो. जेवढा लाईन जनरेट करेल रिॲक्टिव्ह पॉवर कपॅसिटन्स असतो ना, तो जनरेट करतो की नाही. जेवढा लाईन जनरेट करेल तेवढा लोड आणि लाईनचा इम्पेडन्स तेवढं कन्झ्युम करते. Generation and absorption of a reactive power in that case at natural load is a 0. तुम्हाला एक्स्ट्रा काही लावायची गरज नाही. This is one more advantage of loading the transmission line at a SI. The reactive power generated, the reactive power generated in the shunt capacitance of the line is exactly absorbed by the series inductance. खरं म्हणजे इथे अजून एक शब्द पाहिजे, and load if you have connected the inductive load. Net circulating reactive power is a 0. Network. If the line is loaded below its SI, below P is less than P0, a line supplies reactive power to the system tending to, tending to increase the system voltage. मगाशी जे ड्रॉ केलं तर मी फ्लॅट voltage. This is for P lesser than P0. This is for P greater than P0. This is for P equal to P0. Right now, he is talking about now this. If line is loaded below its SIL, what will happen? Voltage level will get boosted up, because the line now supplies the reactive power to the system. Means what? There is an extra or a excess of reactive power flow through the transmission line, which tends to increase the system voltage. And above it means what? If the line is loaded more than SIL, the line absorbs the reactive power, tending to depress the voltage. Why? Because there is a shortage of reactive power. Fine? Okay. We'll see the last point now. I hope जे काही तुम्हाला बेसिक नॉलेज हवा होता before starting the chapter number 3, that is shunt compensation, it will over now once we complete this part. Before starting the chapter 3, we must know its objective. right now why we use shunt compensation, why we use connect or why we connect compensate and shunt passion, क्या ऑब्जेक्टिव्ह आहेत ऑब्जेक्टिव्ह ते तुम्हाला नेक्स्ट लेक्चर मी सांगेनच. पण प्रायर टू ते ऑब्जेक्टिव्ह सुद्धा समजायला तुम्हाला काही बेसिकची गरज आहे, म्हणून हे मी पॉईंट्स घेतले. अँड रिमेंबर दीज पॉईंट्स जे काही का मागच्या आणि आजच्या लेक्चरमध्ये जे काही मी पॉईंट्स कव्हर करतोय ते तुमच्या सिलेबसमध्ये नाही आहे, त्याच्यावरती प्रश्न येणार नाही नक्कीच. बट ते बेसिक गरजेचं आहे. देन अँड देन ओनली यू विल कम टू नो what are the objectives of using the shunt compensation. ओके, कारण पुढे हे सगळे टर्म्स यूज होणार आहेत. आधी हे सिलेबसमध्ये होतं, आत्ता काढण्यात येईल. नाव विल सी इम्पॉर्टंट पॉईंट विदिन पाच 10 मिनिटात संपूर्ण केली. अनकॉम्पेन्सेटेड लाईन ऑन अ ओपन सर्किट. बघा नीट फोकस ऑन दिस. What is saying? Uncompensated, no compensator, right? Normal transmission line. What if there is a no load? Means your line is open circuited. Loaders connect नाही केला, right? Short, remember short transmission line असेल, short transmission line, short distance transmission line काही फरक नाही पडत. But for medium and longer line, there will be one effect called as Ferranti effect. ते तुम्हाला दिसून येईल. Ferranti इफेक्ट म्हटल्यावर तुम्ही एकच स्टेटमेंट वापराल. ऑब्वियसली आय नो यू विल गेट व्ही आर मोर दॅन व्ही एस. रिसिव्हिंग एंड साईडला व्होल्टेज जास्त मिळतो सेंडिंग एंडपेक्षा. रिझन बिहाइंड इट बघूया. थ्रू तुम्ही आय थिंक EPS 1मध्ये कुठेतरी शिकलेला तुम्ही, जस्ट स्टेटमेंट आणि एक डायग्राम. थ्रू इक्वेशन आय विल प्रूव्ह दॅट how you will get VR more than VS. ठीक आहे, हे पण फायनल इंटरव्ह्यूला वगैरे टेक्निकल इंटरव्ह्यूला उपयोगी पडू शकेल. वी ऑल नो व्होल्टेज अँड करंट प्रोफाइल इक्वेशन्स, P of x, I of x, VR cos beta A minus x, जे Z0 into I. रिमेंबर हा टर्म जो है Z0 into I is nothing but VR, and similarly VR upon Z0 is nothing but I. Anyhow, this current phasor is resolved into two components, cos and sin. Bas. And if x equal to 0, it is sending end. If x equal to A, receiving end. If lossless line which is energized by a generator at both end, sending end only, because I consider it as open circuit. Second side, I mean receiving end side la kai nasnar. Receiving end side is a open circuited, and is open circuited at the receiving end. Then IR equal to 0. Solve equation. See, line है. You are connected a generator, sending end side, receiving end समझा open है. या लाइन में करंट फ्लो होगा. This is as good as like this. No load. Single line diagram मध्ये काढायचं चालतं. No load. Circuit is open. Means what? Current flowing through this entire circuit is normally you will say 0. Okay? Or instead, can I say here? Look at this diagram. Can I say as here is the receiving end side and here is the sending end side. If I consider this as a sending end current IS, and let the current flowing here is a IR. Obviously, as it is open circuited, so IR will be equal to 0. Fine. IS is also equal to 0. पढ़ते हैं ना? हाँ? IS is also equal to 0. Anyhow, net current flowing circulating current is 0. Fine. Now what about voltage between these 2 points? Receiving end voltage. Receiving end side ला voltage मिळेल की नाही मिळेल? मिळेल. Let that is voltage VR. Obviously same voltage मिळेल, right? But same voltage current मिळायला नको पाहिजे, because you are connected source and the load through transmission line. Line will also have its own impedance X. Means what? There will be something lost between this series inductance. Okay, ठीक है. Now I will prove you. I will from this diagram at least. From this diagram at least, you can say Vs is equal to Vr. If I assume this Vx is a very small, I'll say approximately equal to Vr. Okay. First thing. Second thing, you said IR equal to 0. Third thing, you said IS equal to 0. Right? Brother, out of, I will now prove you with the help of equation only. I will prove you this is wrong. This is also wrong. Only this one is correct. Prove करूं? Remember, I have considered here JK line consider केलेला मी, that is medium or long transmission line, not applicable to short transmission line. Let me clear. This is applicable only for medium or a longer transmission line when it is fully open circuited or lightly loaded. No load or lightly loaded condition. Okay. We know these two equations. You said I equal to 0. So if I equal to 0, as it is open circuited at resisting end, I equal to 0, just put it here. Jite jite I resistor, jite 0 put kara. What about this equation? V of x will be equal to VR cos beta A minus x. J said 0, I is 0. So this entire term will get cancelled out. Half term 0, you will get only VR cos beta A minus x. Right? Now in this equation, I of x made I cos beta A minus x, I is 0, just put it here, you will get 0, you will get only this term, VR upon Z0 sin beta A minus x. Okay? I know, VR upon Z0 is also IR, but that put up nahi karna. Now the voltage and current at the sending end are given by. Now we'll talk about sending end voltage and then receiving end voltage. Okay, sending end voltage x will be equal to 0, receiving end x equal to A. If I put x equal to 0, V of x will be equal to Vs or Es. At x equal to 0, you are at sending end. Just put it here, x equal to 0, V of 0 will be equal to Vs or Es is equal to Vr cos beta A. If I put it x equal to 0, it becomes only cos beta A. Yes, where theta, beta into A is nothing but theta, I will say it as a Vr cos theta. Now what about current I of x? Just put it here, x equal to 0. It is I of 0 is nothing but Is. Is is equal to J, Vr upon Z0, Vr upon Z0 sin theta. Right? If I put x equal to 0, it will be only beta into Es, where beta into A is a theta. So you will get these two equations, Es and Is. Right? More than that, this J, look at this equation of Is, which is equal to J, Vr upon Z0 sin theta. What is Vr? What is Vr from this equation? Es upon cos theta. Just put it here, Es upon cos theta. This is what Vr. Baki I just sin theta Z0, sin theta Z0. Okay? Es upon Z0 sin theta upon cos theta, obviously tan theta. आताच तुम्ही काय बोललात? You said Is was equal to 0. नहीं. Is is 0 है कहते? नहीं है तो 0. Is a J Es upon Z0 into tan theta. एवढा current flow होणार. But remember that is an imaginary component. काय इमॅजिनरी आहे तेही सांगतो. Here, ES and VR both are in phase. Look at this equation. ES, VR, cos theta. ES and VR both are in phase, which is constant again because there is a no power transfer. मी जे बोललात ना सुरुवातीला ES and VR. पॉवर ट्रान्सफरच नाही आहे त्यांचं मॅग्निट्यूड सॉरी मॅग्निट्यूड आय एम नॉट टॉकिंग अबाउट मॅग्निट्यूड अँगल लोड असेल तरच यांच्यामध्ये डिफरन्स येईल ना. इंडक्टिव्ह डिपेंड्स लॅगिंग लिडिंग वगैरे अँगल कधी येतो लोड असेल तरच ना लोडच नाही आहे ऑब्वियसली बोथ आर इन फेज ES and VR both are in phase and out of IS is differed by angle theta. Okay, आता still you can see here IS is now exact leading the ES by exactly 90 from this diagram. सांगतो कसं आलं. Phasor diagram of open circuited at the receiving end. Okay, the line voltage profile expressed by equation 1 can be written more conveniently in terms of ESC. This V of x can be written as, what is VR? VR is equal to ES upon cos theta. Just put it here. ES upon cos theta, cos beta A minus. Cos beta A minus x, ES upon cos theta is nothing but VR. Similarly for I of x, just put it here VR. इथे लिहिलेच तुम्ही. If we put VR is equal to ES upon cos theta, it will be ES upon Z0 sin beta A minus x divided by cos theta. ठीक है. Now I will try to draw the voltage and then current profile. Right? वरच्या साईडला मी व्होल्टेज फेजर काढतो आणि खालच्या साईडला करंट फेजर काढतो. ओके, अँड हा ॲक्सेस कुठला असेल? दिस विल बी डिस्टन्स. Okay, if x equal to 0, this is a sending end side. I'll write it here. Here x equal to 0, sending end side. Let receiving end side is इथपर्यंत तेवढा डिस्टन्सचा A माइलचा लाईन आहे. इथे रिसिविंग एंड आहे म्हणून समजा. So obviously here x will be equal to A and this distance is A miles. Right? Focus on only equation V of x. Huh? Out of let this is the V of x equation of the focus kara. V of x is equal to ES cos beta A minus x upon cos theta. Okay. Now we are interested in initially in a sending end side. X किती आहे? 0. Put it. X 0 put करा. काय येईल? Cos beta A x equal to 0 means what? Beta into A. Beta into A is theta. Cos theta will get cancelled out with each other. Remaining term is ES. Right? We are getting here ES. Your distance, sir. Okay? Fine? Now do one thing. X आता हळूहळू वाढवत चला. Take your calculator. X आता हळूहळू वाढवत चला. एक काम करा, ठीक आहे, कॉस बीटा ए मायनस एक्स जो टर्म आहे, हां, कॉस बीटा ए मायनस एक्स, यातला मी एक्स आता हळूहळू वाढवत चाललेलो आहे. ठीक आहे. व्हॉट अबाउट दिस एंटायर टर्म ए मायनस एक्स, हा पूर्ण व्हॅल्यू कमी होईल की वाढेल? कमी होणार, बिकॉज इनिशियली ए इज ग्रेटर दॅन एक्स, हळूहळू एक्स वाढवत आहे, मग ती व्हॅल्यू ए मायनस एक्स व्हॅल्यू कमी होत राहणार. ठीक आहे. आता एक काम कर, टेक युअर कॅल्क्युलेटर. कॉस सुरुवातीला एक काहीतरी काढा 45, कॉस 45, आन्सर तुमच्याकडेच ठेवा. कॉस 45 आन्सर तुमच्याकडेच ठेवा, मला सांगू पण नका. ओके. आता 45 जे आहे, 45 वॉज इक्वल टू व्हॉट, ए मायनस एक्स. आता एक्स वाढवा म्हणजे काय, ए मायनस एक्स व्हॅल्यू कमी होईल. 45च्या ठिकाणी आता कॉस 40 घ्या, ती व्हॅल्यू पहिल्यापेक्षा कमी आहे की जास्त आहे? जास्त आहे. आता कॉस 40 घेतलात ना, कॉस आता 30 घ्या, पहिल्यापेक्षा कॉस 45 पेक्षा जास्त आहे. आता हळूहळू हळूहळू ती अँगल कमी करत चला, म्हणजे काय होईल, एनी हाऊ टर्म कॉस ऑफ दॅट टर्म वाढत चाललेलं आहे, म्हणजे कॉस ऑफ लेस अँगल, इन शॉर्ट आय कॅन से कॉस ऑफ लेस अँगल इज अ मोर. गेटिंग मी? म्हणजे नाव टेल मी व्हॉट अबाउट दिस एंटायर टर्म, काय होईल हा पूर्ण टर्म? हळूहळू ती व्हॅल्यू काय होते, कॉस ऑफ वाढत चालली आहे, म्हणजे मीन वाईल म्हणजेच काय, इन शॉर्ट ही पूर्ण व्हॅल्यू वाढत जाणार. बरोबर. इफ एक्स इक्वल टू 0 ही व्हॅल्यू 1 होती, म्हणून जर व्ही ऑफ एक्स वॉज इक्वल टू ई एस सेंडिंग एंड साईड. आता हळूहळू एक्स तुम्ही वाढवत चाललेला आहात, मीन्स यू आर गोइंग इन दिस वे. इनिशियली व्ही ऑफ एक्स वॉज इक्वल टू, आय विल से बघा, 1 into ES. Okay, 1 into ES. In this case, x was equal to 0. Right? Now you are increasing the x. हे ES term आहे तसं राहणार. What about this term? हा 1 असेल आता की more than 1 असेल की less than 1? More than 1. You may get, if you increase x, you may get 1.02 into ES. अजून x वाढवा, 0.3 into ES, 0.4 into EX. कळत आहे? नाव when x was equal to 0, तुम्ही इथे होतात, हां, ॲट ES. हळूहळू ही व्हॅल्यू वाढत चालली आहे. प्रोफाईल कसं येईल, खाली जाईल की वर जाईल? वर जाईल. दिस इज व्हॉट यू आर रिसिव्हिंग. कळत आहे? हे काय होतं बघा, दिस वॉज ES. एक मिनिट. हॅलो, हां, तुम्ही लेक्चरमध्ये. Okay, now you can see magnitude of Vs and VR. VR is more than Vs. This is what the Ferranti effect. Fine. आता अजून एक हेच झालं, हा प्रूव्ह करून दाखवलं मी. व्हॉट, तुम्ही आधी बोललात अप्रॉक्सिमेटली इक्वल टू असतील दोन्ही, VS वॉज इक्वल टू VR, पण नाही आहे, VR जास्त मिळतं. आणि तुम्ही अजून एक शब्द वापरला तर IS इज इक्वल टू 0 म्हणलेलं, ते रॉंग प्रूव्ह करतो. नाव फोकस ऑन द इक्वेशन I of x. इथे लिहिलंय का? फोकस ऑन द इक्वेशन I of x इज इक्वल टू JES अपॉन Z0. ओके, हे तर कॉन्स्टंट आहे. cos theta is also constant. this term sin beta a minus x is a variable, depends on value of x. Just put it here x equal to 0. काय term येईल? If I put here x equal to 0, j es upon z0 tan theta, तेवढा सेंडिंग एंड करंट मिळेल. Value, this is what your is, whose value is equal to j es upon z0 into tan theta. Okay, now you are increasing the value of x. आता परत take your calculator, calculate this term. Sin of beta a minus x. Okay, initially assume this term a minus x is 45 degree. Sin 45 घ्या, व्हॅल्यू कुठे तर नोट डाऊन करून घ्या. हळूहळू ती अँगल आता कमी करा. व्हॅल्यू काय होते सांगा. कमी होते, करेक्ट ना. करंट प्रोफाईल कसा असेल, आयएस हळूहळू हे वाढत जाणार की कमी होणार, कमी होत राहणार, कमी होत राहणार, कमी होत आहे. ओके, कुठपर्यंत कमी होतं बघूया. ॲट रिसिविंग एंड साइड, रिसिविंग एंडला व्हॉट इज व्हॅल्यू ऑफ एक्स, ए मायनस ए साइन ऑफ बीटा इंटू 0, 0 into anything is, so I of x was equal to IR, कारण x equal to a put केला होता, you are getting IR as a 0. कळतं. मग सुरुवातीला जो होता करंट बघा, IS was equal to which is j ES upon Z0 sin tan theta, tan theta. हे करंट हळूहळू हळूहळू कमी होत 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 at receiving end you will get 0. कळतं. गेटिंग मी. पण हा प्रोफाईल आलाच कसं काय, ॲज इट इज ऑन ओपन सर्किट, नो लोड, करंट का फ्लो होतोय, दिसतंय ना. कमी होतो, आय नो. आयरला वेन ॲट अप टू रिसिविंग एंड इट इज 0, इट गोज टू 0. पण सेंडिंग एंड साईडने तरी का फ्लो होतोय, आहे ना करंट. वाय, या करंटला काय म्हणतात, करंट फ्लो होतो दिसतंय. खरं म्हणजे IS 0 पाहिजे होता, ओपन सर्किट आहे, बट स्टील सम करंट इज फ्लो. लॉस, आय राईट वन वर्ड. हे वर्ड तुम्ही पुढे ऐकलं असेल तर बघा. That is what the okay, ठीक. This is called as a line charging current. ठीक आहे. इवन दो तुम्ही लोड नाही कनेक्ट केला तरी सुद्धा लाईन विल टेक सम करंट टू चार्ज इटसेल्फ. त्याला स्वतःला नेहमी चार्ज ठेवायचा असतो त्या लाईन. कळतं. इवन आय हॅव शोन यू, म्हणजे हे काय, हे लाईन इम्पेडन्सवर बघा, हे जे कपॅसिटन्स होते ना लंब डिस्ट्रीब्युटेड सारखे, दिस इज वॉट युअर सेंडिंग एंड साइड, राईट. यू कॅन सी लाईन मे करंट मे फ्लो. हा तर सर्किट क्लोज आहे ना, इथे ओपन आहे, पण हा सर्किट तर क्लोज आहे ना. टू चार्ज these capacities, this is called as a, these currents are called as a line charging current. हे हळूहळू होता 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 इकडे येता येता झिरो मध्ये. ठीक आहे. इवन इफ यू कन्सिडर सिंपल ट्रान्सफॉर्मर, सिंपल ट्रान्सफॉर्मर जे BW शिकला होता, नो लोडला करंट किती घेतो ट्रान्सफॉर्मर? If it is an ideal transformer, it will take magnetizing current I mu. Why? जो कोर आहे त्याला नेहमी मॅग्नेटाइज ठेवावा लागतो त्याला. टू मॅग्नेटाइज इट सेल्फ इट विल टेक सम करंट I mu. If it is a practical transformer, then it will take current of I0, no load current, to cope up with the to magnetize itself as well as to cope up with the some core loss. That's why it will take certain amount of current. Right? Okay. In next lecture, we will start with the actual. हे तुम्ही बघून घ्या बघा तेच केलेलं आहे. We'll start with the third chapter, objectives of shunt compensation. Okay. We'll stop here.